Logarithms with general base. In the introduction, we noted that a to the power b equals c is equivalent to log to the base a of c being equal to b. And we've used this statement a lot. It's a very important statement. The exponential function y equals a to the x and the logarithmic function y is equal to log to the base a of x are inverse functions of each other. So if we have f of x is a to the x, the natural domain of the function is all reals. We have no problem with any input value into a to the x. So any x value can go into the a to the x function, which would have this shape here. This is drawn for a greater than 1. So if this is y is a to the x, we know that the y-intercept would be at 0, 1. We looked at this in the section on exponentials. And if x is 1, then y would be equal to a. The range of the function is that it takes real values, but only those greater than 0, because we know the negative x-axis is an asymptote, so the curve is entirely above the x-axis. The inverse function is log to the base a of x. So if we bring in the graph of that, which is in red here, then it would go through 1, 0 and a 1. And we can get those both by considerations of logs and from the fact that we know that that's a reflection in the line y equals x. So if you reflect 0, 1 in y equals x, it becomes 1, 0, and 1a would become a 1. The natural domain of the inverse of the log function is x is a real, x is greater than 0. Note that apart from the fact that this is x because x is the input, it's the same as the range of the function. The domain of an inverse is always the same as the range of the original function. The range of the inverse is y is reals, and we can see that's the same as the domain of the original function. So functions and their inverse always have this relationship that the domain of the function is the same as the range for the inverse, albeit that we change this to y because that's now the output, and the range of the function is the same as the domain of the inverse.